Welcome back, and this will be our last lesson in the series of lessons that relate to chemical reactions. So today we're going to be taking a look at how energy kind of fits into the whole situation, and we'll get started here in just a second. So I'll share. Oh, yeah, I didn't think that was funny either. So I'll share with you the specific goals for the lesson, and then we'll get right underway. So let's see if we can activate this little share screen doohickey here. There we go. So you got a whole set of lesson goals here. There's some key language, exothermic reaction versus endothermic reaction. You're going to want to kind of have an idea what the differences are between them. Something called activation energy and something called heat of reaction. I'd like you to kind of grasp the idea of what those actually are and be able to interpret them from something we call an energy diagram. And then have an idea what chemical equation looks like that includes energy. We call that a thermochemical equation. Thermo kind of meaning heat energy. So, and the final idea is what is the relationship or what is the effect of a catalyst on the energy of a chemical reaction. So those are specifically the things that we'll be looking at. Let's see if we can't get right underway with the specifics. Okay. So here we have a situation, a couple of ideas. First of all, chemical reactions always have some sort of a relationship with energy. And basically what that means is energy is either absorbed by the products or it's released by the reactants. And we're going to take a look specifically at some language that relates to that. So a couple key terms here. One of them is called a exothermic reaction, where we see energy leaving the chemicals as they react, just like we were leaving a doorway, exiting, exothermic. We sort of have the opposite to that, entering a doorway, or energy entering into the chemicals and being stored. We would call that endothermic. Sometimes we like to say energy is absorbed. So we have sort of opposite circumstances, exothermic energy being released, endo energy being absorbed. And what we know is that there's a specific amount of energy related to chemicals in the form that they exist in. So we call that the potential energy or the energy stored as a result of it being that chemical. Little background before we get started. One of the things that, or too deep into this, one of the things that we should be aware of is the unit that identifies energy. You're probably more familiar with an energy unit called calorie. Calorie comes from the metric system. There is another unit that's more common in the scientific world that we would call joule. Joule would come from what we would call the international system. And joule will be the energy amount that we're going to probably be dealing with in most cases. So typically what you might also see is a unit of energy called kilojoule, which really just means 1,000 regular joules. So those ideas, that's a little background before we get started. Okay, so here we have some ideas that just kind of restate what I talked about. If you look at our diagram here, it shows reactants on the left side and products on the right side, just like we write when we write a chemical equation. And our reactants are higher up than our products are. That means our reactants have more energy stored in them than our products. Well, in order for this to be the truth, reactants would have to let go of some of that energy when they turn into products. So our visual here kind of shows that. It shows our energy being released from the reactants, and what ends up happening is that energy goes off into the environment. Then it's released as thermal energy or heat energy. So what we look for is we look for the position of reactants compared to the position of products. And in this case, the reactants are higher than the products, so energy had to be released from them. What we're going to see is there's a way to represent this numerically, and we would have a negative amount of energy. Even though there's no such thing as negative energy, a negative symbol means energy has been released. So if we do see negative associated with energy, joules or kilojoules, it means energy was released to the environment. It means it's an exothermic reaction. We have the opposite circumstance. our endothermic reaction. So here we're looking at energy being absorbed. If we look at the diagram here, the reactants are lower in energy than the products. The only way that that could happen would be if the products absorbed energy as the reaction happened. So energy from the environment gets absorbed right into the products. And the way we can recognize that in symbol form, we'll be seeing a positive sign, no negative sign, indicating the energy amount has gone up from what it used to be. It used to be a lower amount. It raises to a higher amount. We call that an endothermic reaction when we recognize that. Okay, so here we have what we call our energy diagram. And we're going to look for an idea we call activation energy. And activation energy sort of has a definition. The definition of activation energy might be the energy needed to get the reactants to turn into products. So there's a minimum amount of energy for chemicals to turn into products. If you could imagine maybe a puddle of alcohol on a desk, it would really only take a spark to ignite that alcohol. However, if you had a pile of sawdust on the desk, it might take a pretty hot flame to get that sawdust to begin to burn. That means the activation energy in the sawdust would be greater than the activation energy in the alcohol. So there's an energy amount, a minimum amount. So if we look at our diagram here, we're seeing the reactant particles. They're absorbing some energy like somebody's pushing on them, but they're just not getting enough energy to make it up to the products. So they kind of just stay as their reactants. So it would require more energy. We call that the activation energy. A bigger push would be needed. So we give them that bigger push, and now they can make it up and turn it into products. So once they get that amount of energy, we call that the activation energy. And now products form. They're no longer the same chemicals. They're the same particles arranged in a different way. So the activation energy is determined by comparing the amount of energy that was in the original reactants to the peak, how much energy we had to push with to get over the peak. And when we look at that numerically, that peak, we compare two amounts for activation energy. So we compare approximately 340, which we got by just drawing a line across from the peak all the way across, and then we got 100 from the amount of energy stored in the reactants. So 340 from the peak, 100 from the energy stored in the reactants before we started. The activation energy would be 240 kilojoules of energy. In order to get the reactants to turn into products, any amount lower than this would not cause a chemical reaction. Any amount higher than this, then we have what we call spontaneity. Spontaneous chemical reaction. There's plenty of energy in the environment to allow it to happen. So here we're looking at just a couple of diagrams that show the same thing that we just talked about. Sometimes that activation energy is a real small amount. Sometimes it's a large amount. Well, what's going to happen is it's going to depend on the chemical, but the way that we always determine it, we look at the plateau for the reactant, the flat line where the reactant energy is on the diagram, and we look for the peak. We take the difference of the peak compared to the plateau, and it reveals what we call the activation energy. Another idea that relates to the chemical energy stored in chemicals would be something called the heat of reaction. How we compare the energy stored in the reactants to the energy in the new things that we call the products. There's always a difference in that amount of energy, and that difference we call the heat of reaction with these symbols, Greek letter delta H. So delta H, or heat of reaction. So to get delta H, or heat of reaction, reactants have to turn into products. So we compare the original amount of energy stored in the reactants, the new amount of energy stored in the products, and the difference is called the delta H, or the heat of reaction, the product amount minus the reactant amount. In this case would be 140 kilojoules. Notice the sign is positive. Well, the sign is positive here because this is an endothermic reaction. energy entered into the products. So energy had to be absorbed by the products to get a positive sign here. So we call it an endothermic reaction when the heat of reaction has a sign that is positive. So our delta H is a positive amount in this case. There was a climb from reactants to products in terms of energy amount. So again, just restating the difference between energy stored in the reactants and the products. That's what we call heat of reaction. We compare the two plateaus. The reactant plateau, flat line, where the reactant energy is revealed, right here, and the product plateau, right here. So that's how we would calculate delta H, or heat of reaction. So let's interpret some energy diagrams for the three things you ought to be able to do. Determine, first of all, what type it is. Is it an endothermic reaction or an exothermic reaction? So how do we do that? Well, we look at the reactants versus the products. Look at the position of the products. They are higher in energy amount than reactants. The only way that could happen would be if energy was absorbed. So energy got absorbed by the products as the chemical reaction occurred. We would call that endothermic as a result. So what would our activation energy be? I like to think about this kind of like miniature golfing. If you were to hit this ball on the miniature golf course, but not hit it hard enough, it might go. It would fall right back to where it began because we didn't give it enough energy to get it over the hill. So what do we compare again? The reactant plateau to the peak. So the plateau of reactants to the peak is what we compare, right? 250 compared to 50, and that reveals 200 kilojoules of energy to cause this chemical reaction. We call that the activation energy, or AE. So final question, what is the heat of reaction? Well, heat of reaction is really just comparing how much energy stored in the products, the plateau from the products, to how much energy stored in the reactants, the plateau from the reactants. So we compare them. Notice the sign is positive. The product amount minus the reactant amount, 100 minus 50, we got a positive sign. Well, that's not a coincidence. That's because this is an endothermic reaction. Energy entered into the products or it was absorbed. Let's try one more example. So once again, here's what we're looking for, the reactant and product amounts. Now, if we look, we see energy for products is lower than energy from reactants. That means energy had to be released. So energy got released by the reactants. We call that exothermic. Well, what would the activation energy be? Well, what we do is we look at the plateau for the reactants, compare that to the peak. And then what we do is compare those two, right? Mathematically, 100 minus 40 gives us 60 kilojoules of activation energy. So the activation energy would be 60 kilojoules. Final question, what would be our heat of reaction? We compare our plateaus. Reactant plateau to product plateau. Be careful here now. Product minus reactant amount. Look what's going to happen. 20 minus 40, we get a negative amount. So that doesn't mean there's any such thing as negative energy. That just means energy was released. That's why we're calling it an exothermic reaction. So interpreting energy diagrams, that's one of our goals. You ought to be able to tell me what type of reaction it is, how we determine what the activation energy is, the energy needed to cause the reaction to happen, and how to calculate the heat of reaction. What is the energy stored in the products compared to what it used to be in the reactants? Well, what scientists sometimes do is they will reveal chemical equations that include energy, and we call those thermochemical equations, standing for thermal energy or heat energy. And there's kind of two common ways that this is done. It's a pretty simple idea, but since there's two ways to do it, it can be a little confusing. One way would be to list energy as either a reactant or a product. So on the left side are our reactants, on the right side are our products. If we see energy on the reactant side, we know that energy's been absorbed by reactants. Energy's been added. So we call that endothermic. If we see energy on the product side, then we know energy's been released. So let's take a look at an example. So here we have an example, energy, 572 kilojoules. That's on the product side. So this is revealing an exothermic reaction. It's not a surprise. If we burn the fuel called hydrogen, we will definitely release heat energy. So 572 kilojoules related to the quantities of this balanced equation. So we would call that exothermic. Counter to that, we see now the idea where the energy is listed on the reactant side. So energy as a reactant reveals an endothermic reaction. In this case, to get carbon dioxide and water to turn into this fuel called methane, it would have to store a lot of energy to cause that to happen. That's a pretty difficult chemical reaction to make it occur. But in order to get it to occur, we would need the right conditions. So we would call that endothermic because energy is on the reactant side. Counter to that, down here on the bottom, there's a second way to do this. And sometimes they just use the delta H symbol. So the delta H, and they will reveal either a positive amount of energy or a negative amount of energy. Positive energy means energy was absorbed, endothermic. Negative energy means energy was released. Even though there's no such thing as negative energy, when it says negative energy's been released, we call that exothermic. So here is an example. Here they revealed the delta H. The heat of reaction is a negative amount. So we're just going to call this an exothermic reaction because energy needs to be released to have the idea of a negative value. Counter to that, now we see a delta H value. Delta H is now a positive value. We would call that endothermic. Okay, so let's try this with just a few examples here. Here we have a few examples, and we're looking at thermochemical equation. And it looks like in this method, they're showing us the energy amount on reactant or product side. So energy as a product. So what will that be, folks? Exothermic or endothermic? That's right, exo. That's because energy's been released. It's on the product side. Here we have our energy now listed on the reactant side. So we would label that as endothermic. So energy can be listed as a reactant or a product in one form of thermochemical equation. The second form of thermochemical equation gives you a delta H value, which we covered a couple moments ago. And if the sign is negative, that means energy's been released. So we would call that exothermic. Exothermic, here we're looking at the chemical reaction for the burning of natural gas or methane. Obviously, that would release heat energy, hence the negative sign here. So down below there, we've got a positive sign for heat of reaction. We would call that endothermic. So that sort of concludes the skills for this unit. There's one final idea that I wish to share with you that is really just a visual about a key term. And that key term is what we call a catalyst. So let's clear our drawings. Let's go to that slide. So here we go. So here we're looking at an energy diagram. By the way, it looks to me like this energy diagram is endothermic because the products, I'm going to label it P, products, have more energy in them than the reactants. So energy had to be stored to make that happen. But if you look at the pathway to get, we follow this dotted line, the pathway to get the reactants to turn into products is a lower amount of energy when we have a catalyst present. So this, from the reactant up to the peak, is what we call our activation energy, right? From the reactant to the peak without a catalyst present. Remember, a catalyst is a chemical that speeds up a chemical reaction. What it does is it holds molecules in the correct orientation so they can collide in the correct position, and that will reduce the energy we would need to turn it into products. So a catalyst makes more effective collisions by making the proper orientation. And what that will do is the activation energy will be minimized because the orientation of more of the molecules is the correct one needed. That concludes all of our lessons on the ideas that relate to chemical reactions. And until the next time, bid you well. Have a good day.